Hello, check. Hello. 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 Paling bagaimana ya?
Thank you so much, and thanks everyone for coming. Um, I'll talk about a particular formulation of hydrodynamics that I have been working on recently, namely maximum entropy hydrodynamics. But just to set the stage, um, so heavy ion collisions at the relativistic heavy ion collider and Large Hadron Collider produce a novel state of uh, hot dense matter called the quark-gluon plasma, where the microscopic constituents of protons and neutrons, that is quarks and gluons, they become free over nuclear volumes instead of being confined within the protons and neutrons at ordinary state of matter. A remarkable discovery at heavy ion collision experiments was that this intermediate stage of these collisions of two nuclei can be very well described by relativistic hydrodynamics. So this led to the idea that the quark-gluon plasma that is formed in these collisions are close to states of local thermodynamic equilibrium. But so traditional relativistic hydrodynamics is a description based on macroscopic variables like temperature, chemical potentials, a collective flow velocity, and so on. However, this is not the hydrodynamics that is used to describe the quark-gluon plasma, because this framework, as I discussed previously 2 days ago, is numerically unstable and also has acausal modes. So the theory that is used to describe the quark-gluon plasma is Israel-Stewart type hydrodynamic theories, where along with these variables of usual hydro, the non-equilibrium corrections are promoted to independent dynamical degrees of freedom. So this theory goes beyond the traditional notion of hydro. And this is the kind of theory which has been very successful in describing the intermediate stages or the quark-gluon plasma phase of heavy ion collisions. Now, what was found very recently was that this kind of Israel-Stewart type hydro theories, which can also be derived from kinetic theory or can be motivated from kinetic theory, which does not require the proximity of a system to any local thermodynamic equilibrium. And then this Israel-Stewart type theories can probably describe a fluid even when it's not very close to local thermodynamic equilibrium. However, although this ISH or Israel-Stewart type theories may work far from equilibrium, the applicability is very sensitive to the truncation scheme that is implemented while truncating the kinetic theory from where it is derived. So all standard truncation schemes that are used. Yes.
Yes, that's like the first point, that instability that you mentioned.
Yes.
That was solved by identifying pi equals sigma and replacing sigma dot by pi dot.
Yes.
Is this what we're referring to?
This is what I refer to as Israel-Stewart type hydrodynamics. Yeah. Yes. So all standard truncation schemes that are used in heavy ion collisions are to some extent ad hoc. They either introduce some assumptions which have not no solid grounds, or depend on specific flow profiles which are relevant for heavy ion collisions. So my question that I try to address in this talk is how to formulate a truncation scheme that is based on some concrete principle, or whether it is possible to obtain a macroscopic theory that can serve as some proxy for kinetic theory when it comes to the description of conserved currents like energy momentum tensor or any conserved charge current and so on. So in the first part of this talk, I'll discuss some non-intuitive features in far-off equilibrium dynamics of a multi-component gas. I'll discuss this because some of these features seem to be in violation of the second law of thermodynamics, and I'll discuss how they may be resolved, and then I'll go to the formulation of maximum entropy hydrodynamics and its applications for heavy ion collisions. So let us consider a gas composed of very weakly interacting quarks, antiquarks, and gluons. Now, the model that I'm describing is a very crude model of quark-gluon plasma, but still, for the purposes of this talk, where I'm just interested in showing how some novel non-equilibrium features can turn up, which are in some sort of contradiction to our usual intuition. For that purposes, I hope this will be sufficient. So we assume a kinetic description of this multi-component system in terms of a single particle distribution function, F, which gives the mean density of particles in phase space. So evolution of these distribution functions is governed by some Boltzmann equation, and I take a very simple collisional kernel for the Boltzmann equation. So this collisional kernel specifies the effects of interactions between the constituents of the medium. So this is a widely used but very simple approximation for the collisional kernel, which says that the constituents, all the effect of the interaction between constituents is to drive them towards a state of local thermodynamic equilibrium. So this F equilibrium here is a local thermodynamic equilibrium, which are given by Fermi-Dirac distributions for quarks and antiquarks, or Bose-Einstein for gluons. So this is the setup for kinetic theory. Yes. Yes. So this is basically some time scale over which the distribution function approaches the locally equilibrated form. So it can be motivated from a realistic collisional kernel, but in this model, it's put by hand. Yeah, so this is will be related to some transport coefficients, like the shear viscosity would be proportional to this relaxation time. Pi is the momentum of the ith species, so quarks, antiquarks. Yes. Yes.
Quarks, the relaxation time is the same.
It need not be the same.
Different quark flavors also can be different.
It can be different, exactly. But in this bare bones model, I just assume everything to be the same. So, okay. So once, if I somehow am able to solve for this distribution function, I can integrate over the microscopic momentum of the particles to get the energy momentum tensor or the charge current. So here, the conserved quantity in relativistic systems is not the number of particles, but the difference between the number of quarks and the antiquarks. So this is the conserved current of the system. Now, how to solve this RTA collisional kernel? This is a hybrid description because I have in this quantities like u mu, which is the fluid velocity, or hidden in this equilibrium distribution function, quantities like inverse temperature or chemical potential, which are all macroscopic variables. So this somehow have to be fixed. And also, this collisional kernel by itself does not satisfy energy or momentum. So in order to, so that this collisional kernel satisfies energy and momentum, one has to impose some matching conditions, which means that the macroscopic quantities appearing in this, like u mu, temperature or chemical potential, are related to certain components of T mu nu. So how it is done is, so the way to solve this RTA Boltzmann equation is to compute at each time step the energy momentum tensor and the charge current. From that, find out its time-like eigenvector and eigenvalue, and so on. So that is the just a procedure of solving this. If we want to solve this RTA Boltzmann equation exactly, that is the procedure. We construct the energy momentum tensor at each time step, obtain its time-like eigenvector and eigenvalue. From that time-like eigenvector, we obtain the charge density in the rest frame, and then we match it to a hypothetical equilibrium state to obtain this temperature and chemical potential. So I must state here that although I use symbols like T and mu, these are some sort of, should be thought of as some sort of pseudo temperature and chemical potentials, because these are defined in states which may be far from equilibrium through these matching conditions. Okay. Now, how can I go from kinetic theory to a hydrodynamic description? As I said, if we know the distribution function to some approximation, I can integrate out the particle degrees of freedom to get macroscopic currents, which can be decomposed in this form. E is the energy density in the local rest frame, E is the thermodynamic pressure, capital pi is the bulk viscous pressure, this is the shear stress tensor, and so on. So the important thing to note from here is that all these off equilibrium corrections are related to the deviation of the distribution function from its local equilibrium form. So somehow if we can know how much the medium is away from equilibrium, we can compute this off equilibrium stresses. Yes. Yes. Yes, exactly. So if I want to get some hydrodynamic description from this kinetic theory, I'll start with this RTA-Boltzmann equation and assume that the system's Knudsen number, which is the ratio of the mean free path and some characteristic scale of gradient is small. Here this can be thought of as this quantity tau r multiplying some gradient scale, which is the macroscopic scale in this problem, is of order epsilon, and do a perturbation theory in this parameter. So basically, assume a perturbative series, plug it in, and obtain order by order solutions of this RTA-Boltzmann equation. So this, the 0th order has no gradients, first order has 1 power of gradient, second has 2, and so on. So once we do this, we can just compute the deviation of the distribution function from equilibrium and integrate out the momentum degrees of freedom and obtain hydrodynamic evolution equations for the non-equilibrium currents like the bulk viscous pressure or the shear stress tensor. So here I have not written the complicated coefficients that come out because they are functions of this pseudo temperature and pseudo chemical potential, but I have used some standard definitions here. For example, theta is the local expansion rate of the system, sigma is the velocity stress tensor of the system, omega is the vorticity, and so on. So after this, what we look at, yes. Yes, so if the gradients are sufficiently small, then it will converge. I have to assume the gradients are small. Yeah. This could be anything. Yeah. That is why in the very beginning, I'm saying that. Yeah.
But for things where
Yes.
slightly not the fraction. This one says okay, there's the background on top.
Oh, I see. You're talking about whether this collisional kernel is good enough or not. Yes.
Real interaction, even classic.
Yeah. Yes, that is true. Yes.
And
it is.
Looking at the generics, somewhere this has to fail, but it doesn't describe the product.
Yes. No, it is. It seems linear, but there is some nonlinearity still hidden. Here. It is hidden within these variables like U mu and the pseudo temperature and chemical potentials, which are described by Landau matching. So it is, yeah.
Both are indirectly defined yes.
Yes. So, for example, yes, so U's and T's, the capture quadratic term, whether they capture the correct quadratic term or not is a different thing. Yeah.
They
Yes, they do.
So what
Yes.
is the procedure?
The procedure is at whatever F is, from there I compute T mu nu, the energy momentum tensor. From T mu nu, I define U and whatever temperature and chemical potential that appears here. So basically, temperature, chemical potential, and U mu is some function of F at that point. So,
How does the dimension match?
dimension, so U mu is dimensionless, PP and tau r has dimensions of time or length is the same. So I take
Does some
C to be 1. C, I took this, I set C to 1. So this has the units of time, and this also has the units of time or length. So, yeah. Okay. So, yes.
convoluted form in terms of F.
In terms of F, it has a very convoluted form, although it appears very simple on the outside. Yes.
But the microscopic information is hidden in this relaxation time. So if it's a QG, it have a different relaxation time versus if it is a QPD plasma.
That is, yes, indeed, that is true.
This time is a fixed number.
This is,
It's also a function of.
it's a function of the inverse temperature. It goes as 1 over T.
There also there is some.
There is some F dependence through.
So this is a complicated part of it.
So I will be calculating this only for some specific flow profiles, where like where symmetries restrict my flow velocity to be a certain kind. So for that, I will do this complicated procedure.
Time order of tau r.
So that will happen, say, in the most simplest case, where we take U to be, say, 1. Say we have a system that is homogeneous, but F is anisotropic in momentum. Then we will see that there is no special derivative because take it to be homogeneous. Then it's P mu is energy del delta F. This is also energy, so they cancel out. So then it reduces to del F by del T is equals to -1 by tau r F minus F equilibrium. So there it is, yeah. So in that simple case, we can at least get that notion. Yeah. Okay. So,
Solve order by order in epsilon these equations. How did you get this? By taking all these convoluted forms and all?
yeah. So there, I just take this and I plug it in.
Not. You have write U, tau r, everything in terms of F, and then
Okay. So that we don't have to do. Okay. U and tau are there. Yeah, that we don't have to do.
you said that it's a very convoluted form, so you have to find out the F dependence and then write F as an expansion like that and then solve further.
But the thing is, if in this procedure, I will try to, so at a given instant of time, I will assume that these are at that point just some functions of space-time at that instant. Yeah.
And therefore, small people answer or dependent answer. We are saying normally
Yeah.
can write
Yeah, okay, and then
The configuration space, how you integrate as a different
so this equation I can solve. There is a unique procedure to solve this.
you're writing it as this summation.
Yes.
Normally, I integrate the right hand side and the wrong side. And then normally I solve.
Alan,
Think of this whole thing the base.
but yeah, derivative with respect to x.
Projected on
Yes. Yeah. So, what are you saying about the this one is del del x.
flow line. It's a flow line
Projected along the.
along the flow. Therefore, depending upon the statement is saying that irrespective of the flow line, I get the same answer. Right? But the right hand side answer is not same. It depends on all the things. Yeah. Yeah.
At a given time, if someone has given me this distribution function f, okay, how would I compute u and whatever is here? I would just use that f to compute t mu nu. From that, compute u, evolve to the next time step. Then again, I'll repeat this procedure.
So that means that my question was that the u tau r that are appearing in this quadratic solution down below, they are also dependent on f. So, and there should be an f expansion. I mean, epsilon expansion in those expressions of there. And then you have to collect the right powers of epsilon sides. Because you see, delta f2 has u in it. Right?
Yes.
That u cannot involve the entire f. I mean, that u has to be calculated for a f which has an epsilon expansion. So that is not consistent.
So
That delta f2 definition.
but okay, even if I do it, but that also I can expand in order by order.
You can do it,
Yes.
but the expression will not get this.
So the
Instead of u, you have to write something more complicated.
so
Because you have to
right, indeed, that u and this u are not the same.
I see. Okay.
Yes, yes, okay, indeed.
So this u may be
It-
some epsilon power coefficient of that.
Of that, yes, exactly, yes, right.
And this
Right. Same for
Same is
the
true for
tower.
second
Yeah. Same is true for the second equation. So that is why from this, after I integrate out all momentum, I'll get some t mu nu. That will not describe the same evolution as u and t that is hidden here. It's a that is a different. Yeah. So this notation is I agree.
So are you going to go through this or what are you going to do next?
No.
Some kind of iteration time steps.
Iteration.
See, you have to do the right hand, the complete epsilon expansion to the right hand side. That has to be done, right? Because all those quantities to energy momentum tensor.
Yeah. So this u will be defined from the equilibrium part of t mu. So
I think that is like that will be appearing as a coefficient of certain epsilon power of the original. So of the original you will have to do some epsilon expansion.
Anyway, this delta f1 actually is the order epsilon coefficient of the order epsilon term. So all of this u and tau r should be at equilibrium.
at f equilibrium, yeah. U and tau, yeah.
Yeah.
Yep.
When you go to f2 also, then one has to get tau r should be of getting.
F equilibrium, yes. So okay. So at this stage, we have some hydrodynamic equation which which describes the evolution of components of T mu nu, where these are the off equilibrium corrections: bulk viscous pressure, shear stress tensor. Now we'll take a simple flow profile which describes the early time evolution in heavy ion collisions, namely Bjorken flow, where the medium expands boost invariantly along the collision direction. There is no transverse dynamics. So Vz of the fluid is Z by T. It's called boost invariant because if I boost this profile, I'll get Vz prime, which is Z prime by T prime. So its form remains unchanged. Now, this boost invariant symmetry is best seen in Milne coordinate systems, where the system now becomes independent of the space-time rapidity or this axis. So basically, these are now the changed coordinate system. Here, the fluid appears to be at rest, but it has finite expansion rate, which is given by 1 over tau. So this is where we will reduce the hydrodynamic equations that we obtained. So for this simplistic flow profile, the shear stress tensor has only one independent degree of freedom, which I denote as small pi here. All functions depend only on proper time. There is no vorticity in the fluid. It's just simple one-dimensional expansion. So we have 4 evolution equations for the energy density, net baryon density, bulk viscous pressure, and the shear stress tensor. And the goal is, okay, let's just solve it for some initial condition and see what comes out. Okay, and first I will just quickly say that if we just remove all non-equilibriumness in the system, that is, assume that the system is in perfect local equilibrium, then there is no dissipation. So energy density and net baryon density just for this flow goes as this. This admits a simple scaling solution. And using thermodynamic relations, one can show that the entropy density also obeys a simple scaling function, which goes as 1 over tau. What this means is that in an ideal fluid, the entropy per baryon stays fixed in this fluid element. So here I just plot some lines of fixed entropy per baryon in the T versus mu plane. And in the left, I take a system where quarks and antiquarks and everything is massless. And here I introduce a mass for the quarks. And I'll come to what is the goal of all this, what I'm trying to get at. So in a massless system, there is no microscopic dimensionful quantity. So lines of constant entropy per baryon implies lines of fixed mu over T. So these are all lines that aim for the origin. But once there is some mass introduced in the problem, then initially the system tries to go towards 0 temperature chemical potential, but eventually they go towards the mass scale, which is the mass of the quark in this system. The only thing I want to emphasize here that the entropy per baryon increases from right to left in this plot, irrespective of whether whether the system is massless or massive. Now we add the dissipative part in the hydro part. So here I have, in the left plot, I have added shear stress tensor. In the right one, I have added some bulk viscous pressure as well as shear stress tensor. So first thing, so these are the usual lines of ideal hydrodynamic predictions. Here the solid lines are for ideal hydrodynamics. First thing to note is of equilibrium correction substantially shuffles around these trajectories in this diagram. So, and this trajectories with non-negative initial shear stress that is shown by the dotted lines in both these curves, they lie to the left of these ideal trajectories. Now, this is expected because dissipation produces entropy. So the entropy per baryon increases for dissipative dynamics. And we have seen that the entropy per baryon increases from right to left in this plot. But yes. I took something like 1 GeV. So eventually here, this regime is it's non-relativistic. This regime is yes. it's still close to, its m over t is 1. So here, I mean, yeah, at the higher end. Lower end is not very steep, yeah. And that is why higher end, it behaves somewhat similar to this massless case, but then they they are deflected towards. Yeah. So I want to focus on these trajectories, the dashed lines, which seem to move towards the right, and which seems that it seems inconsistent with our expectations from second law that entropy should increase in a dissipative dynamics. So it was first observed in a much complicated scenario with lattice QCD based equation of state, and it remained mystery for some time that what is going on. Is hydro giving us some wrong result in this for this sort of equilibrium corrections or not? So, okay. So entropy, so here, these lines are for lines of constant entropy per baryon. So they are increasing from right to left. And yeah, and here it seems to go in the other direction, although I have put in dissipation in the system. So then first idea was perhaps hydro is getting wrong results, giving us wrong results in this far off equilibrium cases. But then we solved this RTA-Boltzmann equation from which these hydrodynamic equations we have derived, and we found that such kind of trajectories which move to the seem to move towards the right of the ideal curves also exist in the kinetic theory. So then what is going on? Right? So then it seems that, okay, the statement of the second law is that that entropy cannot, for divergence of entropy cannot be less than equals to 0, but thus initial conditions are here put by hand. Here, they are dependent on the initial condition. They depend. Yes. So, for example, yes. So these dotted ones, they start with some value of initial shear stress. The dashed ones start from some other value of initial shear stress. So then we thought that this expectation that things should move towards the light towards the left of these ideal trajectories is perhaps not correct, because in whatever I have shown for these numbers, I've always assumed the equilibrium definition of entropy, which is for this system epsilon plus p minus mu n over t. But is that justified when the system is far from equilibrium? So then the need arises to compute an out of equilibrium expression for this non-equilibrium entropy. And so we start from Boltzmann's H function. So this is the non-equilibrium definition of the entropy. It reduces to the equilibrium definition when F becomes the equilibrium of Fermi-Dirac Bose-Einstein, or Fermi-Dirac or Bose-Einstein. So this expression can be obtained from the usual Shannon's definition of P log P. It just gives this form. So again, what we do here is, because we were doing some second order hydro, we again expand this distribution function up to second order in velocity gradients. And after that, some algebra, we obtain a second order entropy current, where again, I have not mentioned all these transport coefficients here for sake of brevity. So the important thing to note here is that after this calculation, one finds that this non-equilibrium entropy receives this negative contribution, which depends on the shear stress, the square of the initial shear, or square of the shear stress. So with this expression, we look again at what we saw for our trajectories. So yes, always reduces. Yeah, that the equilibrium entropy is the state of maximum entropy. So any deviation from it should decrease it. Yeah. So here again, we have a look at this trajectory. So this was the ideal trajectory. This was the dotted one, which we were okay with. This one was the one which was suspect. Now, we compute the entropy per baryon along this trajectory and along the dotted trajectory. So for the dotted one, we clearly see it always increases. And so in this plot, these brown curves are the equilibrium, use the equilibrium entropy. And the blue ones use the non-equilibrium entropy that we obtained here. So in both cases, as you just mentioned, because of the presence of initial shear stress, the total entropy now starts from a different point. Before it, both the cases, it would start from the same point. And along the dash trajectory, the equilibrium definition would indeed decrease. That is why it is lying to the right of this curve. But once we include second order corrections in the definition of entropy, we see that its starting value is much lower, so that it rises and keeps on rising. So the total entropy at once non-equilibrium corrections are taken into account never decreases. So at least it shows that hydro trajectories are consistent with the second law. We were just not interpreting it in the right way to start with. So in non-conformal kinetic theory, the same feature goes on. Again, this trajectory moves to the right, but once the full, so here we essentially did not do any order by order expansion. We directly computed this definition of non-equilibrium entropy for kinetic theory. And we see even here the total entropy, once non-equilibrium effects are taken into account, doesn't decrease, but the equilibrium definition, it gives this idea that it can decrease. So with this, it seems okay, hydro is doing fine, but still once one compares hydro and kinetic theory for is very far from equilibrium initial conditions. So here the magenta lines are hydro and blue ones are kinetic theory exact solutions. We see that there is plenty of room for improvement. So this somehow motivates us to go towards a framework which can model both far off equilibrium and hydro regimes with more accuracy than this second order framework was doing that it's working. So this brings me to the second part of my talk, that where we are trying to construct a far off equilibrium theory using the maximum entropy principle. So if we recall, what was the procedure for obtaining the hydrodynamic equations? Procedure was to obtain a distribution function, write the conserved currents in terms of it, and somehow solve order by order. But we need not take that route. We can think of it in the following way, that okay, this conserved current, it has some non-equilibrium corrections. All I need to formulate is evolution equations for these off equilibrium currents. These off equilibrium currents are of course related to the off equilibriumness of the distribution function. So what we can do is, for example, we can take the definition of the bulk viscous pressure, the definition here, apply a co-moving time derivative on both sides, and basically plug in the Boltzmann equation, the exact Boltzmann equation on the right hand side, right? So we can just do this. There is no approximation made till now. And then we see that, okay, without doing any order by order approximation or anything, we can just write down what is the evolution equation of this quantity as it comes out from just by plugging in the Boltzmann equation. So, okay, we took the RTA, and just one can write this out. One can obtain this evolution equation for this non-equilibrium current, the bulk viscous pressure. Similar thing can be done for the shear stress. The catch here is there are certain moments that appear which are not related to any of these quantities that appear in our original definition of T mu nu. Now, this is not surprising, because we have not made any approximation. All this is saying is the evolution of this quantity is connected to some higher order moment of the distribution function, again, one can write down evolution equation of this higher order moment that will be connected to some other higher order moment, and this will be an infinite hierarchy of moment equations. Now, somehow the trick then is to truncate this system of equations. So what is a good truncation scheme? So, okay. So essentially we have to express this delta F that appears in these non-hydrodynamic moments in terms of quantities that appear only in T mu nu. Yes. M is the mass of the particle. Well, no, for massless there is no bulk viscous pressure. Then there is the equation for shear stress. Yeah. So that because that equation is so messy, I have not written it. Okay. Now, all that I have been saying before about this Chapman-Enskog like expansion, gradient, and so on can be reinterpreted in this language. That we do not need to go to all that Chapman-Enskog series, then integrate momentum and that. Just think of all hydro theories that are used in heavy ion collisions in this framework, that finally we have some equation for these non-equilibrium currents. They have to be somehow truncated. Now, in that language, whatever truncation schemes are routinely used, seems that it is based on some ad hoc principles. For example, very popular is the Grads 14 moment, which says that whatever non-equilibriumness we have, just expand it in powers of momentum. Now, this has a feature that for large momentum, this delta F can overwhelm the equilibrium part, and the total distribution function can even go negative. So this, we don't know whether this doesn't seem like a good candidate that can work far from equilibrium. Then delta F motivated by Chapman-Enskog like expansion assumes some collisional kernel, but these two are linear in this in the non-equilibrium corrections here. There is another standard way of doing, yes. The second one is basically obtained from RTA, but then there is some sort of redefinition done. Here one would obtain quantities like sigma or theta, but then one replaces the same trick like the Landau kind of trick to just write this delta F in terms of capital pi uns. So it was originally, the smallness was that there was only one power of derivative, one derivative. There was a expansion rate theta appearing here. There was an velocity stress tensor sigma that was appearing here. So that was the smallness, that it has only one power of gradient. That was a smallness. It was a derivative expansion, but then this Landau kind of approximation is then done so that one can write it in terms of this non-equilibrium currents. So, yeah.
So the first one, you have higher order in terms?
No, then one has to introduce some, then one can have higher order, then one has to introduce terms like pi square or contractions of pi and so on.
Okay, that's fine.
That's fine.
But in principle, it's an expansion.
In principle, one can, yes, can keep on doing it.
It's a derivative expansion, but then after that you redefine stuff for terms.
Yes, and stop only at the level when there is only one power of non-equilibrium thing appearing.
That's just an approximation.
That is an
approximation. It's an expansion.
In principle, it can be carried on. Becomes.
So in this linear approximation, the second one is bigger than the first one.
At least this has some basis that is motivated by some RTA.
First one always will pay. That's why it's not.
Yes,
That's
yes.
what you said, right?
Yeah, that.
So that means means something else must be small in order for it to be a good expression. I was trying to figure out what is that thing that is expected to be small.
That
Now, the second one is a derivative expansion. That's a small quantity for derived.
yes, originally when it was derived, it is always assumed its derivative is small, but then after this approximation, one pushes it to regimes. Yeah. Hmm. Right. And for purposes of heavy ion collisions, there is another approximation where basically it's postulated that let the truncation distribution function be of a certain form, which can take care of large anisotropies in momentum at early times. Again, this is just a postulate. There is no basis per se behind this. Yeah,
That must be a basis.
it's a,
But it's
Some physical reason why you picked up.
this one.
effective use colorless condensate, this kind of an
So this thing I think originally was applied to that kind of system, but then why the distribution function should always be given by this form? It's not. I don't think it's justified. But
Work at certain scale. After some scales that there are dimensions, so the transition does not work. So also at some space get everything. It's just a statement of
yes, and all that is done is in the near equilibrium limit, so that it reduces to some standard hydrodynamic form. But why should one force the distribution function to be of a certain form? I think is
that's based on the system and some cases.
yes. So, and this does well for heavy ion collision purposes for the particular flow profile that dominates the system at early times.
flow profile can be guessed, right? For some initial conditions for this kind of specific flow profile. You cannot have this kind of specific flow profiles if you have some different initial conditions. Some initial conditions may be preferable to give this kind of.
Yes, that I
think probably the CPC kind of initial conditions are preferable to give such kind of anisotropy. Otherwise, you cannot generate such an anisotropy from like free streaming or what you have.
and this does do well in this kind of flow profiles. This one, no, there is no information of mean free path, I think here. Oh, the
I think it's scaled as the other is
yeah, yeah.
related to collision. Not the approximate.
Yes. No, that. So, for example, here one directly writes this non-equilibrium stress, but otherwise, what would appear here is some relaxation time, which is like the mean free path times some gradient. But so that is hidden because one then replaces that with the first order definition and use this as the truncation form. So if one is looking for where that tau r went, that is originally here, but then it is in this framework, it is then done away with this kind of quantities.
This tells you that here shear and bulk dissociation are better expansion parameters than tau r.
than tau r and gradients. Yes.
So if we have more anisotropic system, means your bulk viscosity is more larger compared to all other scales.
More anisotropic than this one. The shear would be much larger than this would be the dominant one. So, okay, what we are trying to say is okay. So this is what we have discussed that. So what we want to do is we want to implement a truncation scheme that is based on some principle which we hope is better than these, and we do not want to invoke any assumptions about the nature of the flow profile that is there. So we want to implement something that can work in more general conditions than very one-dimensional early time expansions and so on. So what we appeal to is this, this one. Okay, I'll use the most probable word also. Yeah. So we want this delta F, this off equilibrium correction, to be expressed solely in terms of quantities that appear in T mu nu. Now, how to construct such a delta S? So we take this entropy root, the most probable distribution that uses all of and only this information provided by T mu nu is the one that maximizes the non-equilibrium entropy, which we introduced before, subject to constraints that that function also reproduces the instantaneous values of the energy density, the isotropic pressure, the shear stress, and so on. So then this becomes a standard problem of using Lagrange multipliers. So we introduce the number of Lagrange multipliers required for each of these constraints, solve this, and then find out whatever the solution of this maximization problem is. We call it the maximum entropy solution, where these quantities in blue are Lagrange multipliers corresponding to these constraints, the energy density, the isotropic pressure, the shear stress tensor. So that A is the static, the takes care of the statistics, Fermi-Dirac, Bose-Einstein, or Maxwell-Boltzmann. So yes, these are to be determined. So I have to choose capital lambda, lambda pi in this gamma, so that with this F equilibrium, I reproduce energy density, isotropic pressure, and shear stress tensor. So that is the interpretation. That okay.
He comes up with the like static formulation. Says that you can get the various partition functions. But then the Lagrange multiplier there, you cannot really, you get the same form, but you do not know how they actually, you do not get a KBT for data. You can call it beta, but it's not really KBT. So that for that you have to use some sort of an equipartition theorem or something. That's why I'm asking, because Maxent just gives you that, of course, you have some Lagrange multiplier, getting a physical issue.
So if I understand correctly, say I have a system where there is no off equilibriumness, only the energy density. Then all of this will go away. But you are saying whether I can still interpret this lambda as a 1 over temperature is still not resolved. Yes. Yeah. No. Indeed, that is true. I mean,
there is some so many of the conventional StatMech people do not really believe in the Maxent.
Yes.
Independently get that's not part of the
yeah, that's true. That in Maxent, one can always say that whatever information you put in, based on that, you get an answer. But I think for this problem, I think because only the information we are working with is T mu nu, probably it's a reasonable principle to follow. So, but yeah, for okay, so right, and also we can show that if one, so here again, nowhere we have assumed that anything is close to equilibrium or gradient expansions or anything. So these quantities have to be computed from these values, and we showed that if you assume that the deviation from equilibrium is small, then this delta F ME, it reduces to exactly this Chapman-Enskog kind of expansion that was done here. So all it says is that in the near equilibrium limit, this process of truncation using maximum entropy will reduce to whatever second order hydrodynamics that I've been talking about from a different approach. So it has some nice features. It is positive definite for all momenta. The most important feature is it has nonlinear dependence on the non-equilibrium stresses, because all of these quantities can be thought of as functions of energy density, the bulk viscous pressure and shear stress tensor, which means if one writes it and then expands it, it will consist of all orders of the non-equilibrium corrections. So that is where it crucially differs from the expansions that are usually typically used in heavy ion collisions, which you can think of as being truncated at only order 1 in the non-equilibrium stresses. So, okay, with this, we also show that the resulted hydroid framework always satisfies the second law of thermodynamics. And also some nice feature is we can systematically follow it by adding, if we know something about higher order moments, we can add that information too and use that as a truncation distribution. But of course, at some level, it gets very numerically challenging. Okay, even at this stage, the maximum entropy distribution consists of 7 Lagrange multipliers. And this is orthogonal to U mu, traceless and all that. So this reduces it to 5. So 5, 6, 7, which are non-linearly related to the energy density and the off equilibrium stresses. Even for these 7 parameters, one has to do a 7-dimensional numerical inversion, which becomes very challenging. So, but somehow we can do better than that. What we can do is we can go to the local rest frame of the fluid where the shear stress tensor is it becomes purely spatial, and our goal is to match these Lagrange multipliers in terms of the shear stress tensor components. What we showed is in the local rest frame, one can think of this, so pi one can think of as a 3x3 matrix. It can be written as a series in this gamma. So gamma is the matrix of Lagrange multipliers. And because it can be written as a series, one can show that the shear stress tensor and this Lagrange multiplier matrix, they commute. So they are simultaneously diagonalizable. Now, and because pi ij by construction is symmetric, it has real eigenvalues, admits orthogonal eigenvectors. What we can do is we can do a rotation so that we go to the frame where pi ij is purely diagonal. We can diagonalize pi there. So this reduces solving this complicated 7-dimensional inversion problem to basically 4-dimensional problem. So which is a simplification, but it's still, I mean, we have not numerically solved it yet. Okay, but we have solved this approach in certain flow profiles, again, looking at Bjorken flow where there are certain symmetries, so which I have been talking also before. So T mu nu has only 3 independent components: the energy density, the transverse, and the longitudinal effective pressures. And here in this restricted flow profile, the maximum entropy distribution function consists of 3 Lagrange multipliers corresponding to these 3 unknowns. So again, just to put it concretely, start with this Boltzmann equation, convert it to evolution equations of energy density and effective pressures. These are not closed because this involves the full distribution function. And here we replace it with the maximum entropy distribution function. So basically we solve 3 equations. Now it has the same, not exactly the same complexity as hydro, because at each time step we have to invert to obtain the Lagrange multipliers in terms of energy density, PL and PT. And then we solve it. And we see that this framework, maximum entropy framework, is in very nice agreement with solutions of kinetic theory. So here I am taking the massless case, there is no bulk viscous pressure. So it shows the evolution of the shear stress as a function of the proper time, which proper time in Bjorken flow. And one finds that these dotted lines are obtained from kinetic theory, and these dashed ones are obtained from the maximum entropy truncation procedure. It is in very nice agreement with the kinetic predictions. And here I also show the evolution of the Lagrange multipliers in units of the temperature, and here is the Lagrange multiplier for the shear stress. All this shows is at late times, the Lagrange multiplier lambda indeed plays the role of an inverse temperature because it's approaching 1. And at late time, the system is isotropizing or thermalizing, hence isotropizing, and hence this Lagrange multiplier gamma corresponding to the momentum space anisotropy is approaching 0. We then went on to a system that has finite bulk viscous pressure, and there also we here plot the evolution of the bulk viscous pressure scaled by the enthalpy density, and similarly for the shear stress tensor scaled by the enthalpy density as a function of proper time. Here again, we see that the maximum entropy framework, which are shown by the dashed lines here, are in quite good agreement with kinetic theory. The only some differences are seen for this orange trajectory, but it starts from an extremely off equilibrium initial condition. And in kinetic theory, there is some early time universal behavior seen in the quantity of this normalized effective longitudinal pressure as a function of the proper time. And here we see that again, maximum entropy very accurately captures the evolution of the early time universal behavior that is found in kinetic theory. So here there is one feature that I would like to point out that, yes, never used the equation of, so the so okay. I never, yeah. Okay, at this level, I have to somewhere write P as a function of E. So I use the equation. So for a massless case, I used epsilon is 3P. For a massive case, I used what we would get for the mass. Yes. Yes. Specific heat. Yes. Del E by del, yeah, del E by del T. So we can compute it, but yeah, that I don't think it will be consistent with what we know, because this, I mean, because of the reason that any temperature that will appear here is not a real, I mean,
There is some money.
no, there is some, yeah.
Like to appreciate how this gets away from what we do.
Okay. Yeah, that's, I think, can be explored, yeah. Yeah. Okay, so how much time? 5 minutes. So, yeah. Okay, so I would quickly point out to this feature that was already pointed out, that in far off equilibrium regimes, this lambda need not play the role of an inverse temperature. In fact, to the extent that it can also go negative. But that does not mean that the distribution function becomes ill-defined or anything. The maximum entropy distribution function remains well-defined once this quantity sigma, which we just obtain, one can just see it from the expression of the maximum entropy, that once that is positive, definite, everything stays fine. But just this fact that this parameter lambda, which seems like a 1/T, can be very different from that when the system is far from equilibrium. And this plays a role in initializing the system with large bulk viscous pressures initially. But I will skip this now because I will go to. It's still normalizing. Yeah, yeah. So, okay, I talked about Bjorken flow. There is another analytically, another analytical flow profile, which can mimic some features of heavy ion collisions, namely Gupsar flow, where the medium expands boost invariantly in the beam direction, but has rapid transverse dynamics, unlike Bjorken flow, which was homogeneous in the transverse direction. So here the feature of this flow profile is such that the medium expands so rapidly in the transverse direction that at late times the system cannot thermalize. In Bjorken, at late times the system was always approaching the thermodynamic limit, local thermodynamic limit. Here it cannot do so, and this provides a good test bed to see how maximum entropy is doing very far from equilibrium. So, so I'll skip this. So here again, we take the same strategy, write down the evolution equation for energy density, and here there is only one independent component, the effective transverse pressure, and do the same procedure of maximum entropy. First of all, we show here that traditional hydrodynamics, the usual ones that are used in heavy ion collisions, second order hydro, so it completely breaks down at large rho. So rho can be thought of as a time. So at late times, the system is rapidly expanding in the transverse direction and cannot thermalize. So these green ones are results of kinetic theory, but the red ones are hydro predictions. And at late times, they are breaking down to the extent that effective longitudinal and or transverse pressures can become negative. So this is one extreme out of equilibrium domain where we see the breakdown of hydrodynamics. Going to third order does something, but it still does not reach the right asymptotic limit for this flow profile. And also for certain initial condition, I cannot even initialize this third order hydro. But the moment we use maximum entropy framework, we see that even at late times, this maximum entropy framework is in very nice agreement with results of kinetic theory. This is an extremely off equilibrium scenario. So it correctly describes both the early and the late times of this flow profile where traditional hydro breaks down. And finally, this maximum entropy idea need not be used to only formulate hydro. It can also be used at the end of the hydrodynamic stage of heavy ion collisions, where the hydrodynamic fields are converted to particles. So basically, there again, the same problem arises that we have knowledge of the energy momentum tensor. How do we reconstruct a particle distribution function that we can evolve after that? Because after that stage, the medium is too dilute for hydrodynamics to be applicable. There again, the same procedure can be formed, can be formulated, and we propose to use this maximum entropy for this problem of converting the hydrodynamic fields to particles. So I reach to my conclusions that we derive some second order Israel-Stewart type hydro for a coagulant non-conformal, very crude model of non-conformal coagulant gas at finite mu v. Certain trajectories which seem to violate the second law of thermodynamics, we provided a microscopic explanation for this behavior and established their consistency. And we derived a far from equilibrium fluid dynamics theory based on Boltzmann equation using this maximum entropy. This scheme has some concrete foundations on which it is based. It can be systematically improved. It obeys the second law of thermodynamics throughout. It does not assume that the medium is close to local equilibrium. And we showed that in certain flow profiles, it accurately predicts the kinetic theory evolution of T mu nu. And, but this has just been formulated. Numerical implementation has to be done, which we plan to do. And importantly, this hydrodynamic principle or procedure can be applied not only to fluids that are typically formed in heavy ion collisions, but also more generally. And then there is an effort to search for non-equilibrium attractors in fluids beyond one-dimensional expansions. And these are other two things that I did not talk today, but talked before, day before yesterday, that to formulate stochastic hydrodynamic simulations and explore its effects for characterization of bulk properties of QGP. And I'm also working on implementing dynamics of critical fluctuations with a goal of modeling the dynamics of a fluid near a phase transition. So I thank thank you for your attention, and yeah. Not yet. That's, yeah. Mhm. Yes, actually, we did explore the range of non-equilibrium values of shear and bulk that it can reproduce. It can reproduce a large fraction of the allowed, but not all. So, yeah. The the allowed region we obtain only numerically. So, but not analytically. So basically, um, there is this space of and there is some allowed region by kinetic theory, and it generates a broad part of it, but not all. So, but that is also a statement that is dependent on the instantaneous value of the mass over temperature, and so for if there is no bulk viscous pressure, then it can generate the entirety. Mm. Right. I mean, yes. I mean, my guess would be speed of sound if we compute from del P, del E, then both pressure and equilibrium will always use some fictitious equilibrium state. But whether a perturbation can propagate faster than light or not, that remains, that I've. Yeah.
But also we can do the restrictions on the parameters.
Yes. Yeah. Yes. Oh, no. Okay. So, what was seen in heavy ion collisions is that this quantities like shear stress, uh, if we look at its time evolution, then irrespective of whatever initial conditions we take, they rapidly converge to some universal curve. So that was called the non-equilibrium attractor for in the perspective of heavy ion physics. So, this we realized what the reason for it was in the flow profile where it was discovered, but it has not yet been generalized to more relevant flow profiles. So that is what I mean here.